All right. Good morning, everyone. Welcome to the fourth annual mini conference of NHERI GSC. I'm gonna read the opening remarks that we have prepared, and then I pass it over to Jordan to introduce our keynote speaker. Good morning, everyone, and welcome to the fourth annual NHERI GSC Mini Conference. Thank you all for joining us today. We are very pleased to have you here and grateful for your participation in the event. Before we begin, I would like to sincerely thank the members of our organizing team, whose time and effort made this conference possible. Parisa, our president, Zul Kazim, co-chair of research, Raji and Tamrakar, chair of community engagement, Narayan Kumar, our vice president, Ali Reza Mir Ghafouri, chair of workshops and mentoring. So this mini conference was created to provide a space for graduate students in the natural hazard field to share their work, exchange ideas, and build meaningful connections. It's not only a venue for presenting research, but also an opportunity to foster collaboration, strengthen community, and support one another as early career researchers. Throughout the day, we will hear from graduate students working across civil environmental engineering, geoscience, computational modeling, data science, and related areas, reflecting the multidisciplinary nature of natural hazard research. We will also hear from participants in the NHERI GSC Interdisciplinary Research and Data Challenge, who will present projects developed through sustained collaboration over the past several months. All sessions will take place through this Zoom link, and we encourage you to stay engaged throughout the day. Thank you again for being here. And it is now my pleasure to pass the floor to Dr. Jordan Nakayama, our user forum representatives and former Secretary of NHERI GSC, who has been involved with the council since its early ages. Jordan, you're up.
Well, thank you, Poria. Good morning, everyone. I am extremely excited to announce our keynote speaker. As his PhD student, I've had the pleasure of working with him for the last 5 years, so please welcome Dr. David Roueche. Dr. Roueche is the Gottlieb Associate Professor of Structural Engineering at Auburn University and the Associate Director for Standards with the NSF STEER Network. He received his PhD from the University of Florida in 2016 under Dr. David Pravat and is an NSF Career Award recipient. So today we will have a Q&A session at the end of his presentation, but if you have any questions during, feel free to drop them in the chat as they come to you and we will address them at the end. Dr. Roueche, the floor is yours.
All right. Thank you, Jordan. Appreciate the invite there. And I just sent a request to share. There it goes. We'll drop that in here. But yes, thank you for the introduction there. And thank you, organizers as well, just for inviting me and giving me an opportunity to come talk to you all. I love the conference, love the theme of it, and looking at innovations. I love the data challenge, going beyond the numbers. And I think that will tie in well to some of the themes that I'll be talking about here. So I've titled my presentation, Are We There Yet? Perspectives on the Past, Present, and Future Value of Post-Disaster Reconnaissance. And like I said, I'm excited to see how this will relate to the themes you already have for the conference. But let me start with kind of some motivation. Where did the title come from? So some of you may know I've got a wonderful family. I've got 4 kids. There's us, and then along with my brother-in-law, sister, and their kid. And so at the end of the semester, we took a couple of days to go up to North Georgia, kind of the Blue Ridge area, and spend a couple of days in the mountains, which was awesome. Had a great time. But as you can imagine, it's about a 3.5-hour drive, so not too bad. And then, you've got the various hikes. So you can imagine one of the phrases that I heard fairly often on the trip was, are we there yet? Are we there yet? Are we there yet? You might be surprised, though, that most of the time it came from my brother-in-law, though, not the kids. But that may be the only surprise there. But that phrase, are we there yet, sort of spurred, the thinking as well about reconnaissance and where we've been and then where we're going with that. And, are we there yet? Have we arrived? So I want to just very, very briefly kind of touch on some of the past of reconnaissance. And forgive me, I know the attendees here probably represent a lot of different hazards and a lot of different interests. My background, of course, is in extreme windstorms and low-rise buildings. So a lot of what I present today is going to be tailored to that. But I think the applications are still very broad. And so I'll leave it to you for sake of time to sort of fill in, the specific examples that may apply to your hazard. But if we go back to, let's say, the one of the fundamental events that really inspired modern hazards engineering was the Lubbock, Texas tornado back in 1970. The amount of fatalities, just the damage that it caused to a metropolitan area, the fact that there was a university close by that had such expertise that could jump in and do a detailed study of that is really what inspired a lot of the growth in hazard engineering since then, at least on the wind side. And if you look at what they were able to do back then with the tools that they had, yes, they took a lot of photos, and then they had to go into a lab and actually develop all those photos from film, right? And that takes a lot of time. They didn't have GIS. They didn't have a lot of the technology they had. But it's really cool to go back to the reports and just see the level of detail and the level of analysis and all that they were still able to do. I included just a couple of little examples here, but I love the one at the bottom right corner from Professor Ted Fujita, looking at these kind of suction spots from the circulation of the tornado and tracking those from aerial photos, and just some really cool stuff that they were able to do back then, even with much more limited technology than we have. And then, of course, you have Hurricane Andrew in 1992, which was another significant event that spurred a lot of change and a lot of reconnaissance studies focused on Hurricane Andrew. One of the really cool ones I thought was Wakamoto and Black in 1993, where again, they're looking at the patterns of damage and what direction things failed in and mapping those out over a large area to sort of reconstruct the wind swaths as the hurricane moved ashore. Again, some really cool analysis with what we would consider today some fairly rudimentary tools that they had available to them. And then we can move on to Hurricane Charlie, the 2004 hurricane season, and we start to see some things that may look a little familiar. I thought it was really interesting back in again 2004, 2005, and they had this Views software, which is actually developed for earthquakes initially. Views stood for visualizing impacts of earthquakes with satellites. And they applied that to Hurricane Charlie, and they're able to overlay these, the red dots represent photos that were taken from a camera in a car, right? The first street view, at least that I saw documented, kind of overlay all that in a GIS platform. So some pretty cool stuff that looks similar to things that we do here today as well. And on the right side was a study by some good friends of mine that were on my PhD committee at the University of Florida, Forrest Masters and Kirk Gurley, looking, they actually used surveys of homeowners, but they're starting to look at things at the very detailed, percent roof cover loss and stratified between different building code areas. And again, some nice work done there that both illustrated some changes that were made in the code, as well as, spurred some further changes that need to be made, but all driven through reconnaissance. And then, of course, there's the 2011 tornadoes. And these were personal to me because that was my introduction to reconnaissance and really not to research in general, but to hazards engineering. This was the Tuscaloosa tornado was the right before my undergraduate graduation. And so the day after I graduated, I hopped in a truck with Dr. Bravatt and headed out to Tuscaloosa and spent the next 3 or 4 days surveying tornado damage and taking lots and lots and lots and lots of pictures. I didn't count my steps back then, but I'm sure I made my step goals, whatever it was, as we walked through all those areas. And we're just overwhelmed, if I can say, just by the amount of destruction and amount of damage that had been caused to those communities, and just realizing the challenge that stood before us as researchers to try to make a difference in these areas. But kind of looking at how we conducted the reconnaissance, like I said, it was lots of walking around using geotagged photographs, to document the damage, and then we would rate those with the EF scale. We had some GIS platforms that we could import those into and get contour maps. The University of Alabama team had a LiDAR that they could employ. So starting to really use some of those modern tools that we use now, and early since there. But compare that, and we could go on to some of the other ones. But then, and I think about even just when I started 10 years ago or so, versus where we are now with the technology and the tools and so on that we have for reconnaissance. It's just amazing what we have available. And I think one of the best examples of that is the Hurricane Ian. We had STEER went out, and we have a lot of building performance, so kind of door-to-door performance assessments that were done. But what was really amazing was just to see, how it came together between STEER and the RAPID, NSF NHERI RAPID program and our facility, and how, they're able to deploy this drone that essentially mapped, as I'm showing up here in the top right, mapped the entire island of Sanibel, the entire island of Fort Myers Beach. And then all of that data is now on Design Safe as orthomosaics, as point clouds that you can just click on, pull up a poetry viewer, and we can measure. We can do anything that we want to interact with that, that data set that's been collected. I mean, it's just really amazing technology and how that's changed over the last few years. I also think about, of course, AI and how common it is now immediately after an event to ingest either high resolution satellite imagery or other aerial imagery, and very quickly run through and get at least a basic understanding of what's been damaged, either through change detection or unsupervised learning approaches, and being able to quickly map out where hotspots of damage, or where potential success stories or and things are. And so this is the Microsoft AI for Good, but there's lots of other programs, and I think surely there's quite a few even here at the conference that are doing some of this work on your own. And then, of course, we have the advent in the last few years of large language models, and how we can now interact and really talk and interact with these models to analyze data. This is just a very simple illustration, but just with the latest ChatGPT, where you could give it an image with the damage and ask it to classify the roof cover type and estimate the percentage of roof cover loss or roof decking visible and loss, summarize that data. And it's not perfect. This is this is the only prompt I gave it, no other training data or anything else. And it actually does a pretty good job of identifying the roofs, identifying what type of cover, identifying the damaged areas, even masking over the areas and getting that back. So there's a lot of potential in these tools that, was just been unthought of just, 5, 6 years, 10 years ago, compared to where we are now. And then one of the other big improvements is the openness of the data through Design Safe, and just all the investment that's been made there. On the left-hand side, again, just to illustrate, is a data set that Jordan has put a lot of work into developing and using, which we call the WIS, the Windstorm Performance data set. This is single-family residential buildings from hurricanes and tornadoes, and we're using a standardized assessment process over multiple events. And so now we can start to look at that intra and inter-event variability and look at what's been damaged over thousands and thousands of structures combined from these events. Then on the right-hand side, you have the really amazing work that was done by Murshad Amini and Daniel Cox and others with Hurricane Ian, the virtual damage assessments, and just really meticulous level of detail and coverage of that project. And again, that's published. These data sets are all there for anyone to go in and learn from and use. And with the data challenge, perhaps some of you even went into some of these and used them for your own work here. So it's really cool just to see, compare that today with what it was in the past, with how hard it was to get access to data. Maybe something was summarized or published in a paper or report, but to have the raw data to work with and the, individual buildings or infrastructure, so on, that was assessed, to have all that available to use in a lot of different ways, is some really transformative things that have happened here in the past few years. So what have we actually done with that? We could go on and on with different examples, but what have we done with that? And I want to highlight just a few things that, just to illustrate that, reconnaissance has made a lot of impact on, as we translate to society, translate to standards and codes and so on that are affecting everyday designs and everyday life. And one of the first ones that came to mind was going back to the Lubbock tornado, and how that really spurred the efforts of Dr. Ernest Kiesling, both that tornado and the 99 Oklahoma City tornado, to develop the National Storm Shelter Association. And then that led into ICC 500, which is a standard for the design and construction of storm shelters. And then that's been continuously updated. You have the FEMA 320 and 361 and so on as well. But that was, again, driven by observations directly from reconnaissance studies. And then you have Hurricane Andrew, and how that so many different reconnaissance studies on that, documenting what failed and why it failed and what the gaps and what should be done better, and then how that led into the development of the Florida Building Code, which was first adopted in 2001, and then became really a model code for the ICC, the International Residential Code, which is used nationally now. And then, of course, you have as one more example, the Joplin tornado, the NIST, the fantastic study done by NIST on that, and then even the study that I was a part of with ASCE, and how those led to the adoption of tornado standards for the first time in ASCE 722. It also spurred the development of a brand new standard, which is going to be ASCE 83, which is a standard to estimate wind speeds for tornadoes and other windstorms. And hopefully that will be out for public comment in 2027. And that spurred, again, directly from what we observed in the Joplin tornado and the various reconnaissance studies that were focused on that. And of course, it's not just the reconnaissance data, right? There's a lot of other than research that happens beyond that to support the findings and understand them better, and then to drive specific changes that need to be made in the various codes and standards. But so much of it is initiated by reconnaissance, and I could say these events become inflection points where a lot of attention gets on them. Engineers go, we learn from these events, and then that translates into further research and then into the codes and standards. So those are just some more focused on kind of codes and standards. But if we look at just building performance overall, we can also see an impact of how things have changed as we've learned from these different events. So this is a lot of data. Let me point out a couple of things. So this is essentially damage trends in single-family residential for hurricanes. So this is taken from an analysis of the WIST that I mentioned earlier. And so every dot represents a building that experienced
Good, how are you doing, sir? Fine, how's it going?
A certain wind speed,
Busy,
or a certain
yeah,
hurricane in the
maintenance.
past.
All right, yeah.
And then the blue line is essentially a
Yes.
5-year moving average of the average MWFRS, or the main wind force resisting system, kind of the main structure, the cladding damage, and then fenestration damage. And then these vertical lines over here, kind of the colored vertical lines, represent different code eras. This is tied to the Florida Building Code. Of course, this encompasses a lot of different events, and so it's not always tied to those exact years when communities adopted, but at least just gives you some reference point. And what you'll notice from this is, if you track that blue line, let's look at the top one, the main wind force resistance system. Do note this is a kind of a square root scale, so we can visualize the changes better in this lowest 10% damage ratio. We see more frequent damage here in the 70s for homes built in the 70s to the 90s. It starts to actually reduce, perhaps tied to some of the changes made after Hurricane Andrew. And then now when you get to the modern building codes, it's very rare to see kind of main structural elements being damaged in hurricanes, which is a great success to be able to go, especially since we've had some above design level events happen recently. Cladding, some improvement, still not quite there. Fenestration, definitely some improvements as well. And again, in modern structures where we've had now impact resistant windows and doors, and shutters are more in widespread use, we've really seen a significant reduction in fenestration damage as well in hurricanes. Same story in tornadoes is a little bit different, right? We don't see that much of a reduction in damage in the main wind force resisting elements and cladding and fenestration. the impact of the codes is not as much there. So we still got some work to do in that area, but hurricanes have certainly made a big difference. The changes that have been made in the last few years. And again, it's reconnaissance data that we can start to visualize these things, how it's changed. And then I'll mention one more example briefly, just because it's a small one, but it was one that was personally involved in. And that was, I showed earlier that we have quite a bit of roof cover loss still occurring. And really the roof cover loss is what drives a lot of the economic losses, right? When shingles are blown off or tiles are blown off the roof, water gets inside the building, and that causes these cascading problems. And that happens even in a lot of modern code compliant homes. Well, we can fix that, right? A sealed roof deck greatly reduces the amount of water that gets inside the building. But right now previously it was only required where the basic wind speed, looking down here, where the basic wind speed was greater than 130 miles an hour. And so some representatives, IBHS and some others, had made a proposal to IRC, the International Residential Code Council, to move this further back, to require sealed roof decks to 120 miles an hour. And initially that proposal failed. And so they reached out to me, and we used the WISP and some other STEER data to basically go back to areas that were in the 120 mile an hour contour or less than 130 miles an hour, like this area here that still had significant roof cover damage. And then they resubmitted the proposal with this data justifying it, and then it passed, right? So it was a direct impact of, hey, we have this reconnaissance data. We've been meticulous in how we collected it, knowing where it's at, and the amount of damage that's been caused when it was constructed. And then that was then sufficient justification to move forward with that code change and then shift the requirement for sealed roof decks back to 120 mile an hour instead of 130. Okay, so again, relatively small change, but that's just a small example of how reconnaissance data can make an impact into codes and standards and improve the resilience of our society. So with that said, I mean, certainly there's been some successes. It's been amazing to see, how the technology, how the infrastructure supporting reconnaissance has changed, and the tools that we have available to us now with AI and the equipment and so on. It's been amazing to see. But are we there yet? Right? That's the question. It's nice to look back and see how far we've come, but is it sort of reconnaissance is not really needed anymore? It's sort of we've got what we needed out of it, and we can sort of focus on other areas. I think to answer that question, we have to go back to a more societal perspective, right? Certainly we've had some successes, but if you look at society overall and look at, this is the NOAA $1 billion disaster data set that many of you are probably familiar with, you still see that, if you look at the number of $1 billion events that have happened, so many of these are in recent years, right? So these are starred here, green, red, et cetera. These, 2011 is sort of the anomaly, but everything afterward has been 2017, 21, 22, 23. These are all recent events that we've had these increasingly costly events. If we look at just hurricanes or tropical cyclones, we see the same trend. This is now represented in just billions of dollars. And we see that, again, a lot of the recent years, 2020, 2024, 2017, is where we've seen the greatest losses, economic losses, economic impacts from these storms. And certainly we realize that, these losses are due to a combination of things, right? It's the losses, or we can relate to the risk, is the juxtaposition of the hazard, the exposure, and the vulnerability, right? And hazard, we can't really do anything about, and it may be changing in a changing climate. Exposure is what it is. It's going to be growing. We may have some impact on that with policies and so on, and building it out at-risk areas. But populations are growing. The number of people in at-risk areas is going to increase. So what we really need to change then is the vulnerability. And I think we understand that, right? That the vulnerability is the knob that we're able to change. But this is not a unbounded, let's just go as far as we can and just make everything, build bunkers out of everything and make it resist anything that can happen. Because we are also faced with an affordability crisis. And this is something that I acutely realize that many of you are going to be facing as you graduate and you get jobs and you're going into different markets and are soon going to be wanting to buy your own home and so on. If you look at the home price to income ratio and just how that has increased here in the last 20 years or so, it's we can't just make everything more expensive without justification for it, right? What is the return on that investment if we're going to increase? And I recognize that this is a very nuanced discussion, and there's a lot of ways that we can, if we're making things a little bit more expensive, maybe with making it safer, there's a return on that investment. There's also ways that we can offset that cost to size of the home and so on. But the point I want to make is that it's not an unbounded, we can't just let's just make everything safe against an EF5 tornado and go from there, right? We've got to be able to, as engineers, think through, okay, what do we need to improve? What is the best bang for our buck in terms of a safer structure, a more resilient community? And that brings me to a quote that I love to use in my undergraduate structural analysis class that I teach, which is that anyone can build a building that stands, but it takes an engineer to have a building that barely stands, right? We operate on the margins of understanding what the loads are, what the resistance is, and building so where we are just strong enough so that we're not wasting resources, wasting money, over designing things because we just don't understand it fully. And if I'd advance that quote maybe a little bit, I might say something like this, right? Anyone can build a building that stands. It takes an engineer to have a building that barely, what's a real goal is not just to stand, but to remain functional after an extreme event at an affordable cost, right? So that's where we could also say it's probably not just the engineer. That's where we need the policymaker, the social scientists, the economists, and others that work together with us to help understand where those breaking points are and how to optimize that. So kind of connecting this, and I know I'm a little bit on a soapbox here, but this does tie back to Reconnaissance, because this is really about what I call what has traditionally been known as value engineering, right? We need to be able to operate where, yes, we want a safe structure, but when we have really high uncertainty, let me kind of walk you through this chart. There's a lot going on, so let me walk you through it. Focus first on kind of this blue dash line and this orange dash line, right? So this goes back to the fundamental limit state function, right? We get failure if loads are greater than resistance. So we want to minimize that area. We want resistance to be greater than loads. When we have high uncertainty in our loads, high uncertainty in our resistance, in order to get a reasonable reliability or reasonable probability of failure, low probability of failure, the means between these two distributions have to be pretty far apart because there's a lot of uncertainty. So we've got to shift we can't really control the load side. So we're sort of shifting the resistance, the assumed loads. We're using load factors. We're using resistance factors that are accounting for that uncertainty. So when the uncertainty is large, the means are further apart, and we're having to design to higher loads, to higher, assuming weaker material strengths and so on in order to get a target reliability. However, if we can reduce the uncertainty, mean maybe stays the same in the load, so this green line and this solid red line, when we reduce the uncertainty, we can get the same reliability, but with a smaller margin between the means. Right. And so the idea is sort of what I'm trying to illustrate with this is that as our uncertainty grows, we're having to use higher factors of safety on things. We're less efficient, we're more expensive, and we're less confident in what we're recommending will truly improve or make a difference in, an individual building, an individual system. And so that's where I think high quality reconnaissance data, high quality field measurements are really the foundation, right? That's the real world data that helps us calibrate these models. That helps us reduce this uncertainty and be confident in what we're recommending as code changes or standard changes or recommending as policies for our communities. And so, again, maybe I'm a little bit biased because I spend so much time in reconnaissance and working with field data, but I really think that the reconnaissance data is foundational to being able to reduce that uncertainty and give us better value engineering, better efficiency. And and I say this because I've been fortunate to have several projects that have been very interdisciplinary. And so one of these is with several social scientists at the University of Oklahoma, as well as with Dr. Lombardo at the University of Illinois, a NOAA project where we were interviewing tornado survivors and trying to understand their thought process and decision making leading up to the tornado, and then even afterwards in sort of the rebuilding phase. And this kind of doing these projects really sort of humbles you in a way at how much we still don't know and how much uncertainty there is. For example, here we are talking with, I'll just call him Mr. Smith, right? And we're standing where his home used to be. He was in the home got blown away in this tornado. And we're talking with him afterwards, getting his experience. And, he's then asking us about the rebuilding process and what options are available and what he should look for. And I know I can go to, IBHS, the Fortified Program, or various FEMA, guidance and so on out there to say, yes, you need hurricane straps, you need anchor bolts, you need this. And I can tell them that it's going to perform better than what his previous home did. But how certain am I in being able to tell them if an EF2 tornado comes through, is your home still going to be there? How much of it's going to be damaged? Are you still going to be safe? What if it's an EF3? What if it's an EF4? How confident I am in those calculations and those numbers that I would give to someone who's trying to make an actionable decision based on my analysis. And you realize just how much uncertainty is there embedded in that process. Another kind of example that I'll go through, if you would allow me, to just, again, to illustrate this point of kind of the uncertainty that we deal with and how it makes a difference when we are dealing with people making decisions versus just publishing a paper on a framework, right? It's one thing to sort of develop a model and make some reasonable assumptions and demonstrate a framework that gets published as a paper. It's another, like we were in this project, where we're trying to communicate individual risk of their home back to them and see how that impacts their decision making and sheltering decisions during real storm events. Now pressure's on a little bit, right? Because I'm giving them information that may be changing how they are responding to a real event. Now, how confident am I in this information that I'm giving them? What are the implications of being overly conservative and so on? So this was a study, again, funded by NOAA, interdisciplinary study that Jordan has worked on as well with me. And what was really interesting going into it, just kind of having this idea of the uncertainty, was, when I first started meeting with the others on the team that were not engineers, it kind of came across as the idea out there was, with our engineering models, we could look at, say, two homes and be able to say, yep, that one's going to fail, this one down here, that one's, let's say the whole roof failure, the roof comes off. That one's going to fail at exactly 138.45 miles an hour, and this one's going to fail at exactly 116.35, right? And maybe a confidence interval of 1 mile an hour on that, right? That was kind of the idea almost, that they looked at us as, hey, we should know exactly what's going to happen in these situations. But in reality, the wind performance of a specific building is a function of a lot of factors. The direction of the wind, the shape of the roof, the orientation of the building, the presence of large doors and overhangs, and the what connections are used and so on. And when we do our analysis as engineers, we may look at these and, with the knowledge that we have, say, maybe 140 plus or minus 20, and then maybe 115 plus or minus 20 miles an hour, right? There's some larger uncertainty bounds around when we would, what we would expect that failure to occur at. And then that's made, even more challenging by the fact that when a storm does come through, particularly in tornadoes, we don't really know what the actual wind speed is, where we're trying to back estimate it from the damage and then trying to learn from the damage to understand when it's going to fail, right? So there's just a lot of uncertainty, a lot of unknowns that we're still dealing with. And the reconnaissance data, the empirical data, is still pretty sparse and uncertain, especially for tornadoes. And then our engineering models may be a little bit too high level and not really considering the level of granularity that we need to get down to the details of, at the individual building level. And so in this project, what we did was, again, that just helped me realize the amount of uncertainty we're dealing with. Now we're trying to look at homes that have not been damaged yet and give the resident some idea of how vulnerable they are. And so we're looking at things like the type of structure, roof shape, factors that we know are important. But then how do we combine those factors into a score or something that we can give them that has, some tie to their actual individual vulnerability? And so that's where we went back to, for now, we went back to the WISP. And we essentially used empirical fragility function using a baseline structure that has a gable roof and laminate asphalt shingles and so on, that we have enough data in the WISP to reasonably generate an economic loss and a life safety kind of composite fragility function that we can use as a baseline. And then once we have that baseline established, then we look at an individual home and we can sort of shift that baseline fragility using weights that are based on either empirical data or engineering analysis or engineering judgment. And so if a home is much weaker, that fragility is going to shift to the left, and then we sort of develop a score that's based on just the median failure wind speed and convert that into a score of some sort that we can then communicate to the homeowner. And with lots of disclaimers, and we send them a report that has, lots of disclaimers about some of the uncertainty, and this is research and so on. Provide them with some of the factors that are going into our analysis, educate them some on the major elements that are affecting the vulnerability of a specific home, and then try to share the score, and then what factors are influencing, what factors are increasing the vulnerability or reducing the vulnerability, and then tying those factors to some recommendations, pointing them to resources they can use to learn more about how to improve that. So, that all sounds good, and I think we've got a reasonable framework for doing that, but it's sort of humbling, though, to look at just how much uncertainty and how many assumptions and sort of engineering judgment we have to use to be able to get down to this level of quantifying the vulnerability of an individual home, or again, you could broaden that to an infrastructure system. And then it's even more challenging when you think about the fact that here, as part of the same study, we asked them a question before we gave them any information of what wind speed do you think your home would suffer major structural damage. So like the entire roof structure coming off or a wall collapsing and things like that. And what was interesting and surprising was that the survey respondents tended to expect major structural damage to occur at lower wind speeds than what our engineering models, the EF scale, and past empirical studies suggest. So on the left-hand side, the box charts here are the distribution of the survey responses. So if they lived in a site-built home, kind of on average, they expected this major structural damage to occur at 100 miles an hour. Well, according to the EF scale, and according to many of our engineering models support this as well, we would expect that sort of damage to occur maybe somewhere around 120 miles an hour. So the public is expecting the damage to occur earlier. So now, how do we communicate that vulnerability to them if we're trying to get them to make safer sheltering decisions, but they're actually under or overestimating their vulnerability, right? Now, what do we do? How confident are we in all this, right? So the implications of that and the uncertainty of it is really challenging. And this is on the right-hand side is sort of the same story, but presented as a fragility function, if you're familiar with those, and how it compared to, say, our best sort of field data from the Joplin tornado. So all that to sort of come back to this question of, are we there yet? I'd say let's I'm not we'll let this next clip answer it. Are we there yet? So that's at least my feelings on it. Are we there yet? Are we done with reconnaissance data? Or are we sort of have we sort of all the innovation we need and then we just kind of continue on? No, I think reconnaissance data is as important, if not more important than ever. And especially because as I sort of wrap up with just a few specific things, especially because with the advent of AI and with the technology, the equipment that we have now, we can really cover a lot of ground when a event happens. But I come back, I love this quote from in one of Henry Liu's papers back in 1989, where it says the best wind engineering experiments for wind damage to houses are those conducted by Mother Nature. And then mentions that there's some pitfalls. And the first two, so they're not conducted early enough, and so you kind of lose out on some of the evidence that's important. And then two, the investigations are too general. In the past, we've had to, cover a large area, like walking around, just taking a lot of the time was spent just taking a bunch of photos, right, to try to capture that data. Well, now, with modern equipment and AI, those first two are largely addressed. We can cover large areas very quickly with street view cameras, with aerial imagery, and then we have the technology with AI to be able to query and sort of learn from that. But what we need to do then is more focused on this next one, the 3 and 4, which is really those detailed investigations and sorting out the evidence and really digging into it. And so kind of comes back to, yes, we've got these great tools and AI and so on and all these models that can learn from this data. But if we don't have good data for it to learn from, we're not going to get good results from that. And so we really need to redouble our efforts in reconnaissance with making sure that we're getting high quality, high depth data out of these investigations that we can then use to train our AI models and learn from the data itself. And so my challenge to you all that are here is get out in the field, help us with that, right? There's always going to be events that are happening locally to you. And so get to know your local emergency manager, get to know your, the local National Weather Service and so on. And I'm not at all advocating for just, disaster tourism. And as soon as the event happens, go clog the streets and just take some photos. Work with us at STEER, work with the Converge, has some fantastic training modules that would strongly encourage you to do before you step out into the field on the ethical considerations of it and interacting with people. But there's something to be said for knowing what you know as a researcher, as an engineer, and then going out into the field and just talking with people, just seeing the data firsthand, the damage firsthand, seeing the impact, and being able to help collect that data to make a difference. And then next, I would challenge you is connect your work to field research. And that's why I love the theme of this conference. And I think you're doing some of that already. But if you just look at field research and design safe, there's 424 published projects that are classified as field research. And I know some of those are just reports of various cases, but there's a lot of just really rich data sets that are published now on design safe. And we need you all to be interacting with that. And so think about what, as you do all the different research and studies and analysis that you're doing, what existing reconnaissance data can you connect with your research? And then let's have some feedback, right? What data do you wish you had, but don't? Can we get that data? And this is where I would love, I sort of had the thought as I was developing this presentation, and maybe I need to talk with the design safe folks about it, but it would be fantastic, I think, to develop a community forum, a feedback loop of some sort where you all that are doing research that maybe aren't necessarily, trained in collecting reconnaissance data, you're not doing necessarily field research, but to have a way of giving us some feedback on what data are you missing? What data would you like to have that could connect with your analysis to help validate it and so on? Or maybe it's just better quality data. But what do you need that those of us that are much more involved in this data collection can help you get? Or could focus on in future events. But try to connect your work to field research, to field reconnaissance, to real world data, if you will. And then just a couple other very quickly to finish up here, just some kind of low-hanging fruit, if you will, or things that we need to address. One is documenting non-structural damage and functionality. This is a home. This is from our street view cameras after Hurricane Laura. And structurally, we would say, hey, this did pretty good. This was an above design level event. It just lost a little bit of a roof cover, but there was no structural damage. Hey, this is a success. Well, we came back to this area after Hurricane Delta, which was just a month later, and this is what that same home looked like. And you can see that they had to strip the entire interior of the home. Drywall, everything was stripped out because of how much water came in from just this roof cover loss right here. And then, unfortunately, they even had that exacerbated by another storm came through and then blew that debris all over the place. So you can just imagine just how frustrated and how difficult that is for these communities to go through things like this. And I would not want to be the person that talks to these homeowners and say, yes, your home did resounding well. That was a structural success. It absolutely was not in their eyes. But we have a hard time quantifying that damage. And so how can we develop better methods for quantifying the functionality, not just the structural damage? And then lossless damage quantification. I could get on a soapbox on this one, but I won't. But going from just a damage rating to a little bit better is component level damage percentages. But what I'd really love to see us all be working on is kind of this lossless, which is really masking out the damage. So that we can go back and learn from it in a lot of different ways. And I could point to some specifics that we are able to do with that. For sake of time, I'll just sort of leave that here. And then lastly is sort of this data fusion and synthesis, right? As we get so much data, that's post-disaster data, but then we also have all this pre-disaster data, LiDAR, imagery, data set bases from counties and so on. How can we fuse all this stuff together in an efficient and accurate way that we can actually learn from efficiently is a really nice data challenge that some have been working on and making some progress, but we still have a lot more work to do in those areas. So again, this is just sort of touching the surface of some of the gaps, some of the challenges that still need to be addressed in reconnaissance data. But I'll just leave you with this, which is, in all the work that we do, remember we're engineers, hazard engineers, I assume, for the most part here. It's right one of the aspects of NHERI. And so as engineers, we are to hold paramount the safety, health, and welfare of the public. And so whether it's through reconnaissance, as I've kind of focused on here, or any of the other analysis and work, great work that you're all doing, let's make sure we're connecting it back to very explicitly with the public, with their health and welfare, making good judgment, good value engineering to them to be able to make decisions based on. I think that what you're learning and what you'll be talking about here in this conference is a great start to that. Hopefully I've spurred maybe some other ideas and questions along the way as I went through this. But again, thank you for the invitation to present here. Hopefully some of what I talked about resonated and made sense to you, and would love to talk about it with you more here in the question and answer time, or anytime. Reach out to me by email if you've got some ideas, and would love to discuss it further. So with that, I will wrap up. Thank you, organizers, for giving me a couple of extra minutes to finish up there.
Thank you.
Thank you. That was awesome. So we do have about 10 minutes here for some questions. If anybody has any that they'd like to ask themselves, feel free to raise your hand. Yeah, Zool.
Thank you, Dr. David. That was a really great presentation. I think when I saw the title, it was easier for me to connect it to the movie, so it really made me interested in the presentation. I have a couple of questions. I think some of them you've kind of answered it along your presentation. So the first part is, what is still missing when it comes to open data, as well as access to some other information that you think would improve modeling when it comes to reconnaissance? And the second part is, I think from your slide 31, when you were asking homeowners questions when it comes to resiliency and all of that. So what is the impact of social or infrastructure justice, particularly for low-income communities, when it comes to using materials that are able to withstand natural hazard to some level, as we've seen over the years? I have more questions, but I want you to answer that before I continue.
Okay, perfect. Thank you. Good question. So the first one, what are we still missing with open data? So as I mentioned, we've made a lot of progress in open data and in how we're able to access it. it could go a lot of different directions with this, but I think one that comes to mind sort of at the top is just the variety of data that's there. Right. I'll be the first to admit that, I personally have focused a lot and others have focused a lot on, say, single family residential. And certainly that is a big part of it. Those are disproportionately damaged relative to other structures. But I think represented in our open data sets, it's sort of disproportionately represented as well. And I think there's a lot of room for more variety in the types of structures and infrastructure, power infrastructure, multifamily residential or commercial buildings. Like our data sets are seen to be, from my understanding, kind of weak in those areas, and I think could be strengthened. So, I would say the variety of the data sets could certainly be improved. And I think if you were to talk still with people who are trying to use the data, I think we made a lot of progress, and Design Safe has done developed some fantastic tools, HasMapper and Tagit and so on, to make that data accessible. But I think there's still even more room, especially in the kind of the data fusion aspect of relating different data sets together, that I think still needs a lot more work. And then going back to, I think it said slide 31, with trying to connect, our assessments to, individuals and kind of talk with them, and then the aspect of, social justice and all. Yes, I mean that is a big concern, because we know that, right, disasters disproportionately affect low income and these other at-risk communities. And so I think that goes back to, again, the value engineering is, we've got to make sure it's our responsibility. If they're trusting us to make a decision, I've got to be confident in the data that I'm giving them, that I'm not just, giving them some suggestions that aren't ultimately going to make a big difference in their specific, their specific home or their specific community, right? I mean, the dollars that they're spending are valuable. They could be spent on a number of different things. We're all, these communities, people are all facing a lot of different challenges and hazards beyond just the natural hazards, right? And so if we're going to want them to make this investment, I need to be very confident that that investment is going to have a return. It's going to make a difference in them. And so, yes, I definitely think those are related, and it's something that could be explored further.
Awesome, thank you. We also had some students that submitted some questions when they registered, and one of those, I think, kind of has been addressed throughout your talk, is this idea of some of the data gaps. But what do you think in terms of your experience in the field? What are the most critical gaps that you've identified that how can researchers address them in terms of, advancing or reducing the uncertainty associated with the things that you've talked about today?
Yeah, those are good questions, and that I tried to address that some in the those last few slides, at least the ones that come to mind for me. Which, again, I admit I'm sort of biased towards low-rise buildings and windstorms, so you may have to think kind of creatively about some other hazards and other types of infrastructure. But again, I think one of the major ones that I really like is the sort of the functionality and interior damage, and I like it for this reason, because I really think that the best way to get that data is actually talking with homeowners, talking with the people who went through it. And so when you do that, that opens up a lot of other possibilities for us to learn from them, and across a lot of different disciplines. So not just engineering or structural engineering, but the decision making, the social aspects of it, behavioral science, that can all benefit from those interactions. And you've seen in the past that in getting that sort of interior, where the damage came, where the water came into the home and how much and so on. Right now, the best way we have of doing that is just talking with people afterwards who went through it. And so I think that's a key gap that, could open up a lot of doors if we can collaborate on things like that and do those more regularly, could help reduce the uncertainty and economic losses. And also, as we found with our, the project that I'm showing here and the other one, we also typically have better access to what the load path is, and these other details that we want that helps reduce the uncertainty. in our empirical kind of data-driven techniques can come again from just interactions with the homeowners themselves. And so I think that's a key thing that hopefully we'll be doing a lot more in the future.
Definitely agreed. Sully, do you have some more questions?
Yeah, sorry.
No, you're fine.
I have two more, I promise. So the first part is like, how do you establish relationship with social scientists to kind of broaden the research area to ensure that it's not just fundamentally advancing science, but also adaptable for the community? And the second part is when it comes to adoption of like policies from data, do you think bringing in insurance companies could actually impact the drive if they see the economic impact?
Yeah. So the first question, so how do we, involve or, work with social scientists? And I think the first thing with that is just, as engineers is just being intentional about recognizing their value, right? The social scientists have a lot of value in what we do. This is not a purely engineering problem. There are definitely engineering challenges that still remain, but to solve them from a societal perspective, we definitely have to work together. And so in my case, some of those connections with the social scientists came kind of more organically, knew someone who then knew someone else who connected us. But then as, I started working with them and then attending, things like the natural hazards workshop, that at the University of Colorado, right? That's where a lot of these different disciplines can meet around the table with the same things. And that's, how me personally have been able to meet a lot and work with them. I think that could be a good strategy for others, but it may be more organic in a different way for you. But I think as engineers, we just have to recognize that we all have our different expertises and strengths and abilities, but we've got to work together as a team on some of these challenges. And then the second part of your question was about insurance companies and bringing them in, and that is important, and it can certainly help with the incentives to mitigate and strengthen. But you have to keep in mind as well that insurance companies operate for profit, and they make a profit as long as they understand their risk and can price their risk. So it is to their benefit to reduce their risk, but as long as they understand the risk and price it accordingly, they can still make a profit. So it can certainly help, and a lot of insurance companies have have been involved in mitigation and in a number of ways that have been very impactful and are very appreciative of that. But it's not sort of the silver bullet solution to it, because some are not really interested at all, because again, as long as they understand the risk and price it, they can still make a profit. And so, some don't sort of take the initiative to try to reduce that risk regardless.
So well, I think it's about time that we should probably wrap this up. Thank you again, Dr. Roueche, for taking the time to speak with us all.